This is a video for AQA Further Pure, First Order Differential Equations, 1.1 Modelling with Differential Equations. Modelling is using mathematical equations to represent real-world situations. If rates of change are involved, then modelling will involve differential equations. Rates of change are often with respect to time t. For example, velocity is the rate of change of displacement x with respect to time t and is given by dx by dt, the rate of change of x with time. However, there are rates of change that are with respect to variables other than time. For example, look at this, the volume V of a snowball with respect to its surface area, and that rate of change would be dV by dA. We use some alternative notations as standard. For instance, you'll see a shorthand dash to indicate differentiation with respect to x, and double dash would be used to indicate the second derivative with respect to x. Also common is the use of a dot notation to represent differentiation with respect to t. Here we've used double dot to indicate the second derivative with respect to t, but we would also use x dot as dx by dt, the first derivative, and if x were displacement, then we'd think about this being velocity and this being acceleration. Let's have a look at a modelling example then. We know that Newton's law of cooling states that the rate at which an object cools is proportional to the amount by which its temperature exceeds that of its surroundings. And so if a room has a constant temperature of 20 degrees C, formulate a mathematical model for this. Well, we can write that the excess temperature then, the amount by which an object exceeds the room temperature, is T minus 20. And that the rate of cooling, so that will be dt by dt, is proportional to that excess, T minus 20. So my rate of cooling will be equal to a constant times T minus 20. However, I expect this to be negative because I would expect the rate of cooling to be a reduction in temperature. Now, T minus 20, if the thing is warmer than the room, T minus 20 will be positive, and I'd really like this to be positive. So I'm going to put a minus sign in front to indicate that this is going to be a rate of cooling. There's that just written out neatly for you. There's the excess temperature, and there's the rate of cooling there. And a reminder that the negative sign indicates the temperature is decreasing and keeps K as a positive constant. Sometimes, when we're looking at rates of change, we want to look at related rates of change. And to do so, we use the chain rule. Look at this example. We've got the volume V of a spherical balloon, and it's increasing at the rate of 15 centimeter cubed per second. And I want the rate at which R is increasing when R equals 10. Okay, so what do we know? We know the rate of change of the volume is equal to 15. And we want the rate of change of radius, we want to know that when R is equal to 10. Okay, we know something about V. We know the volume of a sphere is 4/3 pi r cubed. And that means I can work out dV by dr. Just differentiating that, I get 4 pi r squared. And if I use the chain rule, I know that dV by dt is equal to dV by dr times dr by dt. Now, I know this, and I want to find this. So, dr by dt is equal to dV by dt, that's 15, divided by dV by dr, that's 4 pi r squared. And so when r equals 10, dr by dt is going to be 15 over 400 pi, which is 0.012 centimeters per second. There's that working written out neatly again. We know that, and we want to find that. There we've used the fact that the volume is 4/3 pi r cubed to give us a rate of change with respect to r, and there we've used the chain rule to get an expression for dr by dt. And there we've worked it through to get our numeric value at 10 centimeters. The next video is 1.2 General and Particular Solutions.